Hello, we are GLR IN228, and today I'll be talking about our experiment involving gallium and aluminum. Our goal was to see if the reaction between gallium and aluminum changes or speeds up when exposed to conditions similar to upper atmosphere, and to see how those conditions might affect the structure of the resulting alloy. Gallium is a soft metal that can melt in your hand. When it reacts with aluminum, it creates a brittle alloy that loses its strength. We wanted to test whether this reaction would behave differently in the upper atmosphere, where there's less pressure and lower temperatures. After running our experiment, we examined the samples under a low-power microscope. We did not see a measurable difference in the reaction compared to what happens at the ground level. Unfortunately, the gallium sample was too large to fit under the high-power microscope, which limited how closely we could examine the structural details. Despite that, our observations showed that the overall reaction still occurred, just without noticeable acceleration or visible changes under the conditions we tested. For future tests, we plan to use smaller pieces of gallium and aluminum, so they'll fit under the high-power microscope. That will let us look at the microscope structure in more detail and see if subtle changes appear that we couldn't see before. We also plan to use a lodestone, which is a device that measures how much pressure a material can take before it breaks. That will help us test whether the gallium-aluminum alloy becomes weaker or stronger under different conditions. In summary, our first result showed no major differences, but our next steps will let us collect more accurate data and better understand how the upper atmosphere affects alloy reactions.
Our second experiment was to see if iron filings would become radioactive when exposed to the radiation upper atmosphere. This research is very important because if metals like iron become radioactive, they could pose long-term health risks to astronauts who live and work near them. Understanding this helps engineers choose safer materials or design better shielding. The first thing we did was get 59 grams of pre-war iron filings. We chose iron because it is one of the most common materials used in construction, tools, and spacecraft materials. It is strong, widely available, and is often part of alloys like steel that are essential for space structures. By studying iron, we can get meaningful results that apply to many materials in real space environments. After we got our iron, we measured the radiation of the iron, and then we put them in plastic bags and pushed them right up to the edge of the tube so they would absorb the most amount of radiation. When we got them back, we saw no significant radiation change, so a craft with iron in it would be safe to go to at least 86,000 feet. However, if we wanted to send a craft higher, we would have to do more testing to make sure the iron would be safe.
As a unit, we learned that science doesn't always give clear or dramatic results, but every experiment teaches us something valuable in our gallium and aluminum project. We expected to see a change in how the metals reacted in the upper atmosphere, but we didn't find a measurable difference. Even though the gallium sample didn't fit under the high-power microscope, we realized how important it is to adjust our methods and equipment to get better data. We also learned the value of teamwork. Each person played an important role in setting up the experiment, recording results, and sharing observations. This project taught us how to think critically, stay organized, and stay patient when results aren't what we expect. Most of all, we learned that science is about progress, not perfection, and that every test brings us one step closer to understanding how things really work.